Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T. This is a video lesson for Introductory Transport Phenomenon, a review based on the textbook by Welty, Rohrer, and Foster. We are wrapping up our study of Chapter 1, Introduction to Momentum Transfer, and we are looking at the section on compressibility. So we cover compressible and incompressible fluids in thermodynamics. Generally, we say that liquids are incompressible and gases are compressible. But we want to quantify this because we're doing a really deep study of fluids, so we need to be very certain sometimes about which of these two cases we are referring to. The bulk modulus is one way that we define this. It's also called the bulk modulus of elasticity, and it is the change in pressure divided by the change in volume per unit volume. Or we can do that with density, dP over d rho over rho. We also have with this, though, a related quantity. The acoustic velocity is very similar. Acoustic velocity can be calculated as the square root of dP d rho. But we just defined the bulk modulus that is dP over d rho over rho, so therefore the speed of sound, or the acoustic velocity, is the square root of negative beta over rho. And don't worry about that negative there, because of the beta, that's going to turn out to be a positive quantity. A common case we look at is isentropic processes. Remember from our thermodynamics that means it was reversible and adiabatic. And in many cases, either there's no time for heat transfer or there isn't enough space for much heat transfer. And so this assumption is not terribly ridiculous in those cases. So if we have an isentropic process with a gas, it says that PV to the K power is constant, and K is defined as C sub P over C sub V. And again, this was all in your thermodynamics course. Now, if you apply that PV to the K power and you need to take the derivative with respect to V, or the density, then you end up with C for this isentropic case is the square root of K times P over the density. If we further assume an ideal gas, then the isentropic ideal gas, the speed of sound in that gas, would be the square root of kRT. Now, this sounds like, why are we even bothering with all of this? Well, because air is a very common fluid, and at generally ambient-ish conditions, okay, we find that air tends to be very much like an ideal gas. And there are going to be processes where this isentropic assumption and reversible is not that ridiculous. And so we can make a very, very good estimate of the speed of sound by the square root of kRT. Okay? Related to this is the Mach number. It's a dimensionless number. It's got several ways that we can use this, but the Mach number is defined as the velocity that you are actually traveling divided by the speed of sound, or the acoustic velocity. Okay. Now, I use MA for Mach number, but in our textbook, they tend to use just the letter M. Okay. Since I sometimes use a capital M for other things, such as the molecular weight, I use the MA. Most of our dimensionless quantities have two letters to represent them. Now, there are a lot of ways that the Mach number is useful, okay? And if you are talking about superfast jet travel, you might talk about the Mach number. But we can use this to determine whether or not it is safe to consider a gas to be incompressible. A gas is incompressible, or, close enough that it's not going to make any difference in our calculations if the Mach number is less than 0.2. When the Mach number is larger, we need to consider it to be compressible, and that's going to make our calculations a lot harder. But so this is a really nice, easy calculation that we can do to determine whether or not a gas is incompressible. So let's look at an example, and we want to know at what speeds air could be considered an incompressible gas. Okay, now for this ambient conditions, I'm going to assume that air is 298 Kelvin. For air, the ratio of C sub P over C sub V K is 1.4, and the gas constant in mass units, not mole units, which is equal to the square root of 1.4 times 0.287 kilojoules per kilogram Kelvin times 298 Kelvin. And that is equal to the square root of 119.7 kilojoules per kilogram. But those units are nonsense units. So we need to look at the unit conversions. 1,000 Newton meters is 1 kilojoule, which gets us to 119.7 kilojoules per kilogram times 1,000 Newton meters per kilojoule. Those kilojoules cancel. Now I have Newton meter per kilogram, still not there. So we need G sub C. So G sub C is 1 kilogram meter per Newton per second squared. Now then my newtons cancel. I have meters squared per second squared. So C is 119,736.4 meters squared per second squared. Now the units make sense. We're ready to actually evaluate this. C is 346.03 meters per second. And we want, therefore, for this to be incompressible, the Mach number to be less than 0.2. I can rearrange this based on the definition of Mach number as V over C. So V needs to be less than 0.2 C, where C is 346 meters per second. And so we find that V needs to be less than 69.2 meters per second. Now, just to relate this to speeds, say that you might drive. 60 miles per hour is 88 feet per second, 3.28 feet per meter. So this is equivalent to 155 miles per hour. Okay? It's pretty safe to say that walking and driving through air is going to be considered essentially incompressible. So that concludes our look at Chapter 1. We're going to be moving into the basics of momentum transfer in our next lesson. Thank you very much for your time.